Hello, everyone. Well, good morning.
You are so funny. You are so funny, little boy.
See, he can see me knocking on the desk, and he'll still bark if he hears a knocking. You see, he has such an expressive face. You can tell when he's even thinking about barking. Yeah, he's thinking about barking. I'm gonna knock. I'm knocking right in front of you. It's not the door. It's right in front of you. Oh, you're so sweet. Can I get a num num? Can I get a num num? Num num. Num num. Bugger. Can I have a num num, please? Thank you. Okay. Bye-bye. All right. Oh, we have enough people to start. Great. Okay. So today's lesson is just going to be an extension of the last lesson. So we're just going to get some more practice with those techniques. Good morning, by the way. Hope you're having a good day. Let me just review what we discussed last time. So the topic of the last lesson was diagonal forces. So if you have a diagonal force of strength F that makes some angle theta, you can think about it as being equivalent to a vertical force and a horizontal force simultaneously. And the size of these vertical and horizontal forces, these are called the components, the y component and the x component. To get the size of these forces, we do trigonometry on our force triangle. So this vertical part is F sine theta, and this horizontal part is F cosine of theta. Okay? And then we solved problems in Newton's second law where there were forces pointing both vertically and horizontally. And when something is moving both vertically and horizontally, we have a net force in the x direction, and we have a net force in the y direction. And the net force in the x direction is mass times the acceleration horizontally. And the net force in the y direction is mass times acceleration in the y direction. So there's Newton's second law applies both vertically and horizontally. And so to remind you, the net force in the x direction is going to be the right forces minus the left forces. Okay. And then the net force in the y direction is going to be the up forces minus the down forces. So we discussed something called a free body diagram. And if this is a free body diagram, maybe we have a couple of forces like this, something like this. So let me give these forces just some random numbers. So maybe 100 newtons, 50 newtons, 30 newtons, 60 newtons, 100 newtons, 150 newtons, and then maybe 80 newtons for this one. So the net force in the y direction would be up forces minus down forces. So the net force in the y direction would be 100 plus 50 minus 30. Okay. The net force in the x direction is going to be, we have 3 rightward forces, so 60 plus 100 plus 150 minus 80. Okay, so whatever those numbers end up being, I don't really care. I'm just doing an example. Okay, if one of these forces is unknown, so let's say we had an additional force this way, which is unknown, so maybe it's just called F, then we still include it in the net force, but we just put it in as a variable. So I would have an extra term minus F, for example. Okay? So let's do some examples. That's basically the topic of this entire class. So, so the first example I want to do is I want to do 2 examples of an inclined plane. Okay, so inclined plane with friction. Okay, so the problem is like this. So we have an inclined plane. Let's say that the angle of the inclined plane is 60 degrees, so it's quite steep. And there is a coefficient of friction, mu sub k, that is equal to 0.2. We put a block on the inclined plane, and the block has a mass of, let's say, 2 kilograms. Okay? And what we want to know is, what is the acceleration of the block? Okay? So what we want to do is we want to draw a free body diagram of the scenario here. So first of all, there's a normal force, F sub n. And the normal force doesn't always point up and down. Okay, it points perpendicular to the surface. So because this is a slanted surface, the normal force is slanted. Okay, we have the weight force. Okay, and the weight force is going to be m times g, so 2 times 10. It's going to be 20 newtons. And if we assume that the block started at rest, the block is going to slide down the incline. Now, because the block is sliding down the incline, friction, which is an oppositional force, is going to point up the incline. All right? So F sub k points up the incline, like that. If the block happened to be sliding up the incline, so for example, if you kicked the block up the incline, it would be pointed, friction would be pointed down the incline, okay? Because friction is an oppositional force. Okay, so in this case, we have a diagonal acceleration. So what we're going to do is we're going to actually rotate the picture. We're going to go like that. And so if I rotate the picture, you can see that the block is actually accelerating horizontally in this rotated picture. So, and furthermore, kinetic friction points to the right, normal force points up. So the advantage of, if we look at the problem from this perspective, we have two diagonal forces. So we would have to do trigonometry for both of these forces. And the acceleration is also diagonal. Okay? But if we rotate it like this, the normal force and kinetic friction are not diagonal anymore. It's now the weight force that is diagonal. So we've basically traded having two diagonal forces for just one diagonal force. And so that fewer diagonal forces makes the problem easier. So we rotate the paper like that. Okay? Now, if I rotate the paper so that the incline is level, I had to rotate it 60 degrees. Okay? So all of these arrows are getting rotated by 60 degrees. Okay? Like that. So I rotated the weight force by 60 degrees. So that means that that angle has to be 60 degrees. Okay? And so now I've got to take this diagonal force and I have to I've got to take that diagonal force and I have to break it into components. So this component right here would be 20 cosine of 60 degrees because it is adjacent to the angle. This one is going to be 20 sine of 60 degrees. Okay? So the next step, what we want to do is we want to redraw our free body diagram with, all the forces being vertical or horizontal. If something is diagonal, we write it as two forces, okay? So I'm actually going to crunch the numbers. 20 cosine of 60 is 10. I don't need to crunch the numbers on that one because I know cosine of 60 is 1/2. 20 sine of 60 is 17.3 newtons. So I've taken this diagonal force and I've turned it into two forces. Okay? And then I have two unknown forces. There's the normal force and there's friction. Okay? So I'm going to start off with Newton's second law in the y, and I say that in quotations, the y direction. So the y direction is this direction, but because I've rotated the paper, the y direction isn't actually vertical. It's actually like a diagonal direction. Okay? So the net force in the y direction is going to be up forces minus down forces. One of these forces is a variable, okay? So we have up forces minus down forces, normal force minus 10, equals mass times the y part of the acceleration. Now here's the thing. The block isn't leaving the incline. It's not accelerating away from the incline. So the y acceleration is 0. So we have normal force minus 10 is equal to 0. This is an important point because usually one of the components of the acceleration is going to be 0 because it's not moving in that direction. So in this case, it's not moving in the y direction. So we conclude that the y acceleration is 0. That allows us to get the normal force, which is 10 newtons. Okay? Now, if the normal force is 10 newtons, what does having a... So someone type this into the live chat if you know the answer, and I will wait. What does knowing the normal force allow you to calculate? It lets you calculate an additional unknown. So which force depends on what the value of the normal force is? Excellent. Friction. So in order to calculate friction, we need to know what the normal force is first. So that is why I usually do the vertical Newton's second law first, because if I did the horizontal Newton's second law, the net force would be F sub k minus 17.3, but I don't know what friction is, okay? So once you know the normal force, you can then calculate friction, which is coefficient of kinetic friction times normal. Okay, so that's going to be, the coefficient of kinetic friction was a given, it's 0.2. So that means that it's 0.2 times 10. So that's going to be 2 newtons. So this is 2 newtons. Okay? So now I do Newton's second law in the x direction. Type it into the chat if, based on this free body diagram, you can tell me what the net force in the x direction will be. Okay? So I have net force in the x direction equals mass times the x acceleration. Now keep in mind that the block is moving horizontally. So we have a sub x is not equal to 0. The block was not moving vertically, but it is moving horizontally. So we do have an x acceleration. Okay. Still waiting on someone to tell me what the net force in the x direction is equal to. While I'm waiting, I will go ahead and put the right-hand side of Newton's second law in. So I have 2a, because the mass of the block is 2. Very good. So I see 15.3. Actually, it's negative 15.3 because remember the net force is right forces minus left forces. So it's going to be 2 minus 17.3. So that means that 15.3, negative 15.3 equals 2a. All right. And so I have minus 15.3 divided by 2 is negative 7.7 meters per second squared is the acceleration. So the negative sign just indicates that it's going down the incline, okay? So that's our final answer. I'm going to do another example because I'm still not convinced that 100% of you are understanding yet, so why not? We've got time. Like I said, there's not really any additional content for today. It's just more practice with these methods because I know it's a little bit tricky. Okay, so let's do a similar example. Let's suppose we have an incline that makes an angle of 70 degrees. It's a very steep incline. Okay. And we have a block that is at the bottom of the incline this time, and we'll say that it's a 3 kilogram block, okay, the coefficient of kinetic friction of the block with the incline is 0.4, okay, and you kick the block so that it has an initial velocity of 5 meters per second. So it's actually sliding up the incline, and eventually it's going to come to a stop. Okay? And we want to know, how far is the block going to slide before coming to a stop? So it's headed up the incline at first, and it comes to a stop, and we want to know what is this distance that the block slides. Okay? So this is a problem where we're going to have to do all the analysis in terms of forces to get the acceleration. And then once we have the acceleration, we're going to have to go to a kinematics equation. Okay? So doing my free body diagram, I've got normal force going perpendicular to the incline. I've got weight force, which is 30 newtons, going straight down. Now, what is the difference between friction in this example and in this example? So type it into the chat if you know the difference in how we're going to treat the friction force in these two examples, okay? I will say in Spanish, ¿cuál es la diferencia? ¿Cuál es la diferencia? Opposite directions, very good. So we're gonna, because the block is going up the incline, friction now points down the incline. So we've got friction which is going in this direction. All right. So now what we want to do is we want to rotate our picture so that friction is now, or so that the incline is horizontal. Okay. And in rotating the paper, we had to rotate the paper by 70 degrees. So that means that this, all the arrows got rotated by 70 degrees. Okay. In particular, the weight force got rotated by 70 degrees. Okay, so I can get the components of the weight force. I will do that really quickly. So 30 times cosine of 70 is 10.3 newtons. Thirty times sine of 70 is 28.2 newtons. Like that. So now we redraw our free body diagram. Okay. With this diagonal force being now two forces, one of them vertical and one of them horizontal. So the normal force is going to be F sub n. Then we have a downward 10.3 Newton force. Then we have friction going this way. And we also have the 28.2 Newton force going this way. So notice how in the previous example friction was pointed to the right, but here we have friction pointed to the left. So we have two left forces and no rightward forces. Okay, now because the block is not accelerating vertically off the incline, the up forces have to equal the down forces. So that means that these two are the same. So I'm sort of I'm doing Newton's second law in the y direction, but I'm kind of skipping a step because I know that the up forces are going to be equal to the down forces in order to make the acceleration in the y direction 0. Okay? So that means that the normal force is 10.3, which allows me to get friction. F sub k is mu sub k times normal. Okay. All right. Mu sub k is 0.4. And the normal force is 10.3. So that's what? 10.3 times 4 is going to be what? 41.2. So that's going to be 4.1 newtons is kinetic friction. So this is 4.1 newtons. So who can tell me, type it into the chat if you know, what is the net force in the x direction now? So the net force in the x direction equals m times a sub x. We'll wait. Negative 32.3, very good. So we have two leftward forces, so it's just going to be minus 4.1 minus 28.2. Okay? Equals 3a. So that gives us minus 32.3 equals 3a. So that's going to be about 11. 10.8, so negative 10.8 meters per second squared is the acceleration. Okay, so that's our acceleration, but that's not what the problem is trying to solve, okay? The problem is trying to figure out how far up the incline is this going to go before it comes to a stop, okay? So, all right. So what we have is we have that the acceleration is minus 10.8 meters per second squared. Okay. We know that the initial velocity is 5 meters per second. We know that the final velocity, because it comes to rest at the top, is going to be 0 meters per second. And we know that the x value is what we're trying to calculate. So go ahead and type it into the chat if you know which kinematics equation to use. Okay? We can think about that as delta x. All right? One thing I recommend, and this is a really useful thing to do when you're studying physics, is just take a blank piece of paper, and when there's a general formula that you're going to use, just put it on that blank piece of paper. So you have a piece of paper with all of your key equations, and you don't have to flip through your notes repeatedly. That's really useful. It's going to save you a lot of time in searching through your notes, okay? If you want to talk about that in the Zoom classroom, we can talk about how to, what equations I think should be on that sheet at this point. Yeah, it's the third one. So we have v final squared equals v initial squared plus 2a delta x. So 0 equals 25, that would be 5 squared. 2a is going to be minus 21.6 delta x. So I can solve for delta x. And we get that it's about, delta x is approximately 1.2 meters. Okay, let's do some more examples. Okay. Here's an example that is pertinent to football, or just pertinent to fighting in general. Okay. All right. So, and I'm just going to do the problem first, and then we'll come back. We'll circle back and see why it is useful in the context of fighting someone. Okay. So let's suppose we have a flat surface. Okay. And we have a block on that surface. And we'll make it a 20 kilogram block. Okay. The coefficient of static friction, okay, the coefficient of static friction, so the block is not moving, we're talking about static friction, is equal to, let's say 0.8, okay? You are pulling on the box with a force that has an undetermined strength F. So it's an unknown applied force. The size of the applied force is unknown. And the angle of the applied force is 30 degrees. Okay? So what we want to know is what size applied force will make the box budge. What size applied force will make the box budge and start to move? Okay? So when we do our free body diagram, in this case, we are going to have this diagonal force, which has an undetermined size F, that's at an angle of 30 degrees. We're pulling to the right, so that means that static friction is going to point to the left. And we have a 200 Newton weight force, which is going down. So that's m times g, 20 times 10. So the reason that this is a little bit tricky is that when we get our components, this is going to be F sine of 30 degrees. This is going to be F cosine of 30 degrees. Okay. Now, these are variables, okay? F is a variable, so our free body diagram is going to have a lot of variables in it, okay? There's going to be more variables this time. So let's see. I'm going to make this coefficient of friction a little bit less. Let's make it 0.7. So I'm going to redraw my free body diagram. I have 200 newtons going down. I have static friction going to the left. Okay. And upward is F sine of 30 degrees. Sine of 30 degrees is 0.5. Okay, so the upward force is 0.5 F. So see how I had to leave it as a variable because F is unknown? So the vertical component of this force is 0.5 F. That's a little bit tricky, okay? I'm leaving it as a variable because we're trying to solve for what is F. The cosine of 30 is 0.87. I think it is. Let me double check. Yeah. So that means that the rightward force is 0.87 F. So again, F is a variable. So who can tell me what is the net force in the y direction? Okay? Or give me an expression for the net force in the y direction based on this free body diagram. Okay, while I'm waiting, the net force in the y direction would have to equal 0 because the box is not being lifted off the surface. Okay? Almost right. So there's a response in the chat that's 0.5 minus 200. Can anyone correct that? Because this upward force isn't 0.5 newtons. You want to tie it back to what I said here, where sometimes the force is a variable. Okay? So excellent. So the net force in the y direction. Oh, I forgot a force. Who can tell me what force I forgot? Why did no one stop me? I forgot a force. I was a bad, bad boy. Who can tell me what force I forgot? There's one more force. Yeah, okay. So there's normal force going up as well. Okay? So this should have normal force going up as well. So there's two upward forces. So who can tell me what going off of the correct response that's in the chat, what is going to be the normal force? Okay, no one's answering, so... Oh, excellent. Cool, we got a response. So the net force in the y direction is normal force plus 0.5 F, okay, minus 200. So solving that equation, and this equals 0. So solving that equation means that the normal force is going to be equal to 200 minus 0.5 F. Okay? So that is going to allow us to calculate the maximum static friction. So notice how the maximum static friction actually depends on what the applied force is. Okay? So it's going to be mu sub s times normal. So it's going to be 0.7 times the quantity 200 minus 0.5 F. Okay? 200 minus 0.5 F. So I'm going to distribute that through. 200 times 0.7 is 140. 0.7 times 0.5 is 0.35. So that's my maximum static friction. Okay. Now here's the thing. Okay. The horizontal component of the applied force, so I'm going to write this out. The horizontal component of the applied force must exceed the maximum static friction for motion to occur. Does that make sense? So you have to at least beat static friction to make something budge. So that means we must have the horizontal applied force, which is 0.87 F, has to be greater than the maximum static friction. The maximum static friction is 140 minus 0.35 F. So we can actually solve this equation. I add 0.35 F over to the other side. So 0.35 plus 0.87 is what? 1.22. Let me double check that. 0.87 plus 0.35. Yeah, 1.22. So 1.22 F has to be greater than 140, which means that F has to be greater than 115 newtons. Okay? So if the applied force is greater than 115 newtons, then the box is going to budge. Okay? Now, here's the thing that's interesting about this. So I want to circle back to talking about fighting. Okay? What if you had applied a horizontal force? Okay? If you had applied the force horizontally, instead of at an angle, what would be the force? Okay? So in this case, the horizontal force would have to be greater than, let me just calculate it really fast. The horizontal force, oops, I didn't even move the paper. If you had applied the force horizontally in the same scenario, so instead of applying the force at an angle, you applied it horizontally, the force would have to be greater than 140 newtons. Okay? So do you see, by pulling at an angle, you reduce the amount of force you have to apply to make the box budge. Why is that? It's because when you pull at an angle, you reduce the normal force, which reduces friction, which makes it easier to pull the box. Okay? So how does this apply to fighting? Okay? If you're fighting someone and you want to push them back, you have to overcome static friction to push them back. Okay? So if you want to push someone back, what you want to do is you want to get underneath them and push up at an angle, which will then reduce static friction so that they are easier to slide backwards. You get what I'm saying? And furthermore, what's going to happen to your normal force if you're pushing upward, according to Newton's third law, then that person is going to be pushing downwards on you, which is going to increase your normal force. So you're going to have more friction. So by pushing upward on an opponent, you're actually giving yourself a friction advantage so that you're able to slide someone back more easily. Okay? So that is my lesson for today. I was going to do another problem, but it's running long. So I will see you guys in the Zoom room.